Oh yeah, maybe before we get started, one thing I'm curious about is, can folks maybe give a show of hands if you looked at yesterday's exercises? Okay, cool. General like temperature in terms of the like length of that exercise set, did that feel kind of like a lot for, given the content that we covered Monday? Did it feel like it was pretty doable? Did anyone try doing basically like all of the questions?
Where were the questions?
They're on zkIAP.com.
Oh, I didn't see.
Yeah, maybe like gesture with hands, like this is like, oh, this was like overwhelming and way too much and I didn't feel prepared for it. This is like, I feel like I could understand the questions and basically approach them, and then this is like the questions were super easy and like I basically just skimmed through and ripped through them. So high, medium, low, medium-ish. Okay, cool. All right. I'm going to keep calibrating, and also, like we mentioned at the beginning, are we also at 2:05? Okay, cool. So we can start. So, one second. Is this a little better for folks on Zoom? Can you hear us, or it's still muffled? Hello, hello? Okay, cool. All right, so, yeah, as I mentioned at the beginning of yesterday's lecture, the remaining lectures of this program are going to be delivered by like a combination of different specialists with expertise at different parts of the stack. So that kind of like exercise format might not stay consistent, but in general, everyone will have something for people to try out after each session that should be related to the content and should hopefully be like a helpful understanding check. All right, let's get started with today's session. So first off, some quick housekeeping items. For the remainder of this week, we've got two more things going on. First is that Jason is going to be hosting ZK Machine Learning Office Hours tomorrow from 5 to 7 in the same room. So if you're curious about what that's all about, then please drop by. It's a super fascinating topic. I've also included a link in the lecture notes for today with like a aggregation of a bunch of different links out to talks and articles and stuff like that about zkML, and I'm sure Jason has many more as well. And then on Friday, Yufei is going to be presenting ZK Math building blocks, so the building blocks behind things like elliptic curve cryptography, pairing-based cryptography, and stuff that's eventually going to build up to next week's session on polynomial commitments. So a few quick updates on the schedule for next week are Monday, I said that we might do our informal office hours on MLK Day. We actually realized it's non-conflicting with the lecture time, so we're just going to do both an office hour session as well as session number 4 on Tuesday. And Tuesday is going to be Circom 2, which is kind of the continuation of this topic with Vivek. Any questions about scheduling, housekeeping stuff? Okay, cool. So as a reminder, all of the course material is available on zkiap.com, at least everything that can be consumed asynchronously. So that means slides, recordings, lecture notes, and exercises. So I'll just go there real quick. Yeah, so this is the website. Again, you can find all of the relevant links here. And again, all of these housekeeping items and scheduling items you can find like on this page. One quick update as well about communication is that previously we had said that we would try to move most announcements to Discord. We got some feedback that some folks don't check Discord super regularly. So what we're going to do is we're also going to send those announcements out over email to a Google group that we've created with folks who are coming in as full participants. So you can expect that to be maybe like an email every 2-ish days following along with the pace of the class. And of course, you're always welcome to unsubscribe if that gets too annoying, or feel free to filter emails, etc. We'll also post announcements about things like, for example, sometimes other folks in the ZK community or adjacent math or CS communities have things that might be relevant. So we'll be sharing those as well to that mailing list on those like regular update emails. Yes, question? Oh, our private. Oh, let me update the link. Sorry about that. Let me do this, because I can't update zkIAP right now. I'll put it in the slides, which you should be able to access also locally. Cool. And, oh, yeah, also, I'm going to try to enforce this a little bit better, but names before questions. What was your name again? Sorry, Fareed?
Yeah.
Okay, cool. Thanks, Fareed. Yes?
Ilya, where do I find the links to Discord and Google?
Yeah, so Yulia asks, where can you find links to the Discord and the Google group? These should have been emailed out to everyone who filled out the sign-up form and responded to our confirmation email indicating that you were going to participate fully in the course. So if you just go to zkiap.com and email this email address, zkiap2023@0xpark.org, then someone, likely Michael, will get back to you.
Thank you.
So I'm also seeing questions in the chat about audio. Is everything okay there, or should I can switch mic to? Okay. Cool. Yeah, so email announcements will come in addition to Discord announcements, and that Discord will open up like in this second half of the week. Okay, so, oh yes, one more question.
Chris, so Discord and email is the same thing?
Yeah, so Discord and email, at least the Discord announcements channel, we're going to post that stuff to email as well. However, we have asynchronous discussion channels in Discord where you can pretty much reach the staff members at any time, and we try to be quite responsive in looking at those channels. Usually what's happened in like previous learning groups is people inevitably start dropping things like articles and links and discussing like, oh, I had trouble understanding this concept, or like, hey, I saw this circuit and I don't understand like what this line is doing. And what we want to do is just have that kind of general chat room open for people to be able to ask questions, have discussion. Yeah, does that make sense? Cool. And then again, for folks in the Zoom, any questions, drop them in chat. And then Isabella, if you wouldn't mind, like just kind of waving me down to check when someone's posted something. All right, so let's get on to the main topic for today. First, what we're going to do is we're just going to do a quick review of some of what we talked about last week. After that, we're going to go into just coding a bunch of circuits together in the Circom/snarkjs tool stack. And then finally, there's some stuff that we didn't get to on Monday, which I've appended to the end of today's session, which is a few kind of like high-level ideas around ZK applications that exist in the wild currently. So first off, as you'll recall, last time on Monday we discussed this idea of zkSNARKs, zero-knowledge, succinct, non-interactive arguments of knowledge. As a quick refresher, these are new cryptographic tools that allow us to generate proofs of pretty much execution of arbitrary computations, arbitrary functions. These proofs are zero knowledge, i.e. like they hide the inputs to the computation. They are succinct in that the proofs generated are sublinear, usually logarithmic or constant in the size of the computation or constraint system that we're proving satisfaction of. They're non-interactive, so they don't require multiple rounds of prover, verifier interaction. And finally, argument of knowledge, don't worry about that one for now, just from an intuitive sense. And the way that we can frame what a zkSNARK does is basically you can prove satisfaction of some constraint system that has public variables and private variables. And using this kind of decision problem format, you can also prove that you've executed a function properly with private inputs and a public output. So for example, if I wanted to prove that I've executed the SHA-256 hash function on some secret input, I might take a function f that takes in a candidate hash output and a candidate hash input, checks that the input does indeed hash to the output, and like accepts if that is true. And then if I prove basically that I have some inputs x and w, such that f of x comma w is true, then that's equivalent to showing that I've like computed the SHA-256 hash function correctly on some secret input that only I know, but everyone can see the output that I'm claiming I know the pre-image of. And this was kind of like the last slide that we got to before we took off for the day, which was this idea of like, how do we actually do this in practice? And my claim basically was that what people have figured out how to do is generate these efficient ZKPs for certain sets of very general problems that it's easy to like compile down any other problem or program or function into. And the specific kind of, this is not exactly true, but the claim that I kind of made was that, that I made is like, one such problem is the problem of proving satisfaction of a bunch of equations of the form xi plus xj equals xk, or xi times xj equals xk. So where all of the like xi's are elements of fp for some like specific system level prime p that's very large. So again, the general process here is like, suppose that I have some function whose execution I want to prove in zero knowledge with all those zkSNARK properties. What I'm going to do is I'm going to write down some series of equations, like I, the zk programmer, will write down some series of equations that look like this, that are equivalent to the function being executed correctly. And then I'm going to prove satisfaction of that system of equations, proving that I know some solution. And then a verifier can come in, they can inspect, like first they're going to want to be convinced that the system of equations that I've written down is equivalent to the function. And then secondly, once I have my zero knowledge proof, they're able to verify that I've basically executed the function because I've satisfied these equations and the equations are equivalent to the function. So what we're going to do is we're going to actually carry out this process, first abstractly and then in zkREPL, for a number of useful functions that people care about. So the first function that I want to look at is this very simple toy function, f of x, which is a function that takes in 4 inputs, x1, x2, x3, x4, and computes x1 plus x2 times x3 minus x4. So what is a zkSNARK proof for this function kind of mean in plain English? Well, what it basically means is that, suppose I've got some number over here out, right? The zkSNARK says, I know some secret tuple x1, x2, x3, x4, such that the result of x1 plus x2 times x3 minus x4 is out. And here's basically a proof, or almost kind of like a signature of that computation that proves that I know such a tuple without telling you what the tuple actually is. Now, this is by itself not a super interesting function, but it's going to be useful for demonstration purposes. One reason it's like not that interesting is because if I give you a value of out, it's like not that hard for you to back out like candidate for tuples. But again, for the purposes of this exercise, we're just basically looking at like how do we build like some sort of ZKP for this function, given the like zkSNARK abstraction. Any questions up to this point? Yes, name? Mm-hmm.
So for verification of this, you're just plugging into the equation. How's that like sublinear? Like what is it sublinear with respect to?
Oh, so the proof that's going to be generated, like regardless of how big this equation is, like right now this equation has a very small number of terms. If it had a huge number of terms, it would basically make very little difference in terms of the eventual size of the proof that's generated and the amount of time it takes the verifier. So kind of, the best in class is going to be protocols that generate a proof of the same size regardless of the length of the computation, and verification takes the same time. Other protocols might have like, time that is like logarithmic in the size of the computation. And size of the computation we'll also define later. Other questions? Cool. Okay, so again, the goal here is to transform that function into a series of equations that look like A equals B plus C and like C equals D times E, stuff like that. So what I'm going to do is I'm going to break down how I, as a human, would actually execute this function if I was going through and like operating on some specific value. So the way that I would do this is I've got my 4 inputs, x1, x2, x3, and x4. The first thing I'm going to do is I'm going to compute some intermediate value y1, which is x1 plus x2. Then what I'm going to do is I need to multiply that sum by x3. So I'm going to set this other temporary variable y2 equals y1 times x3. And then finally, my output is just going to be that second intermediate value minus the fourth input value. So out equals y2 minus x4. So this is how I would like perform this computation as a human. Let's look at what the SNARK machinery is going to see from the perspective of generating one of these proofs. So the idea here is that the SNARK is not going to understand this notion necessarily of running the calculation backwards or forwards. The SNARK basically is just a proof of satisfaction of some constraints. So to the SNARK, what the SNARK machinery is going to see is it's going to see 7 variables, x1, x2, x3, x4, y1, y2, and out. And basically, the prover's output is a signature that should only be, like a proof that should only be valid if the following 3 equations are true. y1 equals x1 plus x2, y2 equals y1 times x3, and y2 equals out plus x4. And out is something that's going to be basically like revealed to the verifier. So what the SNARK proof is doing is it's proving, like the literal statements that are being proven are just that the prover knows some 6 values satisfying these 3 equations for a particular public value of out. Does it make sense why proving that I know some solution to this set of equations is equivalent to proving that I've executed this function? Cool. Any questions up to this point? Because this is sort of like the critical thing that's kind of most confusing about going into the ZK programming model.
Basically like back substitution.
Back substitution?
Yeah, like so if you substitute the definitions of y1 and y2, and you get then you get x1.
Yeah. So basically, there's this equivalence here as a result of we've defined y1 and y2 in these ways, and therefore we can write these equations about them, and this is true if and only if this is true. Yes, Ilya.
You said that, yes, Ilya. You said that out is revealed to the verifier.
Correct. So the verifier is getting a proof that the prover knows 6 values satisfying these 3 equations for a particular value of out.
Okay. And typically, you would be using an equation that's more complex, so you wouldn't be able to reverse the values out.
Right.
From the output. Okay.
Well, it sort of depends what your use case is. We'll get to this a little bit later. But yeah, basically, the other thing that you have to be careful of is if you care about actually hiding some inputs, then the function you're computing had better be a function for which you can't back out the inputs as well. But sometimes you actually don't care about that. You just care about getting a succinct proof of computation, and we'll talk briefly about that later. Okay, so here's a concrete example. Maybe my inputs are 2, 4, 8, and 5. I'm going to calculate y1 is 6. It's 2 plus 4. y2 is 48. It's 6 times 8. Out is 43. 48 minus 5. That's the computation that I do first as the prover. Then when it's the prover's time to generate a proof, what they're going to do is they're going to basically prove, they know some 6 values satisfying these 3 equations. These are the actual values that the prover sees. The verifier doesn't see anything. The verifier just gets a very short proof that they can be convinced of that the prover has satisfied these equations. And that machinery is also what we're going to be talking about over lectures 5 to 9, what actually is the zero-knowledge protocol for this constraint satisfaction problem. But today we're just going to take it as a given that we have that as a black box. Okay, so in some sense, with this toy example, I was kind of cheating because previously I told you, all right, the only kinds of equations you can prove are plus and times in a prime field. Oh, also implicitly, all of these values are going to be let's say numbers in FP. But I'm sort of cheating in this example because I've obviously picked this function to be really easy to express as a bunch of plus and times operations. Yes, Vivek. Yeah, so FP is the prime field with P elements, or it's the finite field with P elements. P is basically a protocol parameter. So for the specific zero-knowledge protocol that we're using for this constraint satisfaction problem, we're going to pick some specific prime field that has particular properties. In everything that we're doing today, we're going to be using, we're going to be in FP, where P is this specific 254-bit prime called the baby jub prime, and you can read more about that prime in the elliptic curve group that it comes from in the lecture notes. So yes, good question.
So you have to, so the prime, like the prime has to be like, I don't know, special in order for zkSNARKs to work over.
Yes.
Modulo that prime in a nice way.
Yep. Yep.
So you can't just pick like a really big number and hope that
Yeah.
zkSNARK will work.
Generally, like the thing that you care about is that like, and again, we'll go into this in more detail later on, but that prime P is, I believe, the group order of a pairing-friendly elliptic curve. And I think also that not all pairing-friendly elliptic curves work. But there's more details about this in the lecture notes if you're curious now. Yifei, is that right? Okay, cool. All right, so anyways, what happens when we have computations that involve operations that can't as easily be broken down into plus and times? Well, for example, let's take division, which in this case we can interpret as, let's say, like, modular inverse. So if my function was instead f of x equals x1 plus x2 times x3 inverse, or let's just say divided by x3 minus x4, then suddenly it becomes not so obvious how I go from that just linear, like, top to bottom computation into just an equivalent set of constraints that map one-to-one with every iteration of the computation. So again, what I'm trying to prove is I know some 4 values producing an output such that, like, out equals x1 plus x2 divided by x3 minus x4. And what I want to show on the next slide is that it's still possible to write an equivalent constraint set for this function. In the previous slide, what we had was, y2 equals y1 times x3. And that was sort of like the step when we were doing the computation going forwards, and then we were able to write the equivalent constraint, y2 must be constrained to equal y1 times x3. In this case, when we're doing the computation in the forward direction, we're setting y2 to equal y1 divided by x3. But I can write an equivalent constraint that still is phrased like as an arithmetic constraint by writing y1 equals y2 times x3. So now what you see is that, like, these constraints don't exactly, follow along, like, semantically the same way that the computation is done. However, it's the case that, like, if you look at these 3 equations and you look at this function, you ought to be convinced that this is true if and only if this was done correctly. Does everyone understand this? Any questions about this equivalence? Okay, cool. So again, we're going to prove that these, like, what the snark is proving is that the prover knows 6 values satisfying these 3 equations, and then a verifier looking at that can be pretty convinced that, like, oh yeah, this, like, reflects this computation. All right, so now we're going to go ahead and get into some coding. So we're actually going to do this stuff in zkREPL. Oh, yes. Yeah, so that is a that's something that we have to be pretty careful around in general. Like, one thing that you'll notice, however, is that, like, if x3 is 0 here, then I guess y1 has to be 0. And, like, you're probably not going to be able to satisfy that constraint. There are some cases where you might be able to satisfy this first constraint, like if x1 and x2 happen to be negatives of each other. If not, like, in practice, what you're going to want to do is, like, add some extra checks about, like, certain values are or aren't 0, and we'll also show how to, like, write equations that do that. That's a really good catch, actually. I've never been asked that about this, but yeah, so we have to be careful. This also demonstrates, like, a class of, like, particularly nefarious bugs in zkSNARK circuits. One problem that happens a lot is, like, you write a system of constraints and you're, like, not actually writing something that's, like, equivalent to the function. In particular, you might, like, forget a constraint, or you might have dropped something, or you might admit, like, a degenerate solution. And in those cases, that leaves your, like, cryptocurrency anonymizing mixer vulnerable to, like, attacks where someone comes in and, like, drains all the money because they provide zkSNARK proofs of, like, invalid stuff. Okay, so let's go into zkREPL now. So basically, what you're going to want to do is you're going to want to go to zkREPL.dev, And what this will do is it'll pull up an in-browser IDE. This was built during a previous learning program, and it's a very helpful tool we found for like rapidly iterating on and debugging circuits, which is what those constraint systems are sometimes called otherwise. So when you pull up zkREPL.dev, you'll see that there's basically like an editor on the left side and this like column that displays logs and stuff on the right side. On the left side, what we're going to do is there's a bunch of stuff going on here, so we're going to just go ahead and delete everything like after signal input A and B. And then we're also going to delete these include statements. And yeah, that's basically what we're going to start with here. And we're going to build up our like original function from scratch. So the first thing that I want to note here is these two lines, signal input A and signal input B. What these are is they're sort of like our variables in the constraint system that we're going to prove satisfaction of. So in our case, we have 7 variables that we care about: x1, x2, x3, x4, y1, y2, and out. So the thing that I'm going to do is, like, if I want to generate like zkSNARK machinery for proving that function, first I'm going to like instantiate these 7 variables. And one other thing that I'm going to do here is Circom allows me to specify which of my variables are public to the verifier, i.e., like, along with the proof, the particular instance variables of like that output are published. And by default, the remainder of the inputs are going to be private. So here I can specify that like that 7th variable out should be revealed to the verifier when a proof is generated. And the last thing that I'm just going to note here is that like this is just this kind of helpful, quirky feature of this zkREPL.dev browser IDE. This is not like a general Circom language feature. But one thing that's really nice is that zkREPL allows you to like test your circuit very rapidly on inputs in this comment JSON format. So one thing that we can do after we write our circuit is we can try it out on those like specific values that we'd put in the slide example. Okay, so now we've declared our variables. Now what we need to do is we need to write our constraints. So again, these are our 3 constraints. Y1 is x1 plus x2, y2 is y1 times x3, and y2 equals out plus x4. So basically we can just go ahead and like write those equations down. So the syntax for writing a constraint is you use the triple equals sign. So y1 triple equals x1 plus x2, y2 triple equals y1 times x3. And then finally we're going to write out, or I guess another way that we can write this is, y2 triple equals out plus x4. And we can see that that, matches with the 3 constraint equations that we had on our slide. Okay, so what we've basically done is we've defined our variables, we've set our equations. Now let's go ahead and generate the various zkSNARK proof artifacts. So let's put in the test values that we'd had previously. So that was 2, 4, 8, and 5. And then we had y1 is 6, y2 is 48, and out is 43. Okay, so once you've put in some test input, you can compile and run the circuit by hitting Shift-Enter. So if I hit Shift-Enter, then what you're going to see here is basically everything went okay, Circom safe, which means that this was they were able to generate like the artifacts for a zkSNARK protocol from this, and we'll go into those artifacts. Vivek will go into those artifacts, particularly in the next lecture. And that for this particular set of inputs, it's able to generate a proof. Question, yes.
Yes.
Name also? Madars, yes.
Your 2485, all those are in strings, like a Circom example.
Oh, you have to do triple?
Yeah.
Oh, wait, so you have to do triple equations?
Real quick, Josh, one sec. So, yes, the reason is because this is going to be interpreted as like a JavaScript object, and since we're working in a prime field, like JavaScript will like run out of precision once I get past a certain point. So it's going to interpret these as big ints. You can put numbers, but then you're going to run into problems if you're using like big signals that go past like the like JavaScript floating point, precision safety limit. Cool. And yeah, Joshua, did you have a question?
Wait, so you have to use
Triple equals.
You have to use triple equals.
Correct, yeah. So we press Shift-Enter, and you can basically see all this information. You can see all these like artifacts. What's going on under the hood is that zkREPL is compiling this constraint system into a set of like protocol parameters, what's called like the proving key and the verifying key. And then it's going to try to generate a proof for that specific input that it satisfies this constraint system. And finally, for good measure, what we can also do is we can write the version of the circuit that has the like division instead of multiplication. So for that version of the circuit, we had that was y2 equals y1 divided by x3. So we're going to write the constraint y1 equals y2 times x3. And just to make this like easier, maybe I'll just like fudge the values a little bit. And I'll be like 6 plus 4 divided by 5 minus 1. 6 plus 4 is 10. 10 divided by 5 is 2. 2 minus 1 is 1. And I can hit Shift-Enter. And again, everything went OK. Circom's safe. So one thing that we can also do is we can test what happens when we put in like some invalid value. So these are 7 values that don't actually satisfy our equations. I hit Shift-Enter. I get fail, error, assert, failed. What that means is like, so there wasn't any issue with compiling this constraint system into a set of zkSNARK artifacts. However, it wasn't able to generate a proof because these values don't actually satisfy the constraints. Yes, Ilya.
So the triple equals are asserts?
That's one way to think about them. Sorry? Oh, yeah, the question was, are the triple equals asserts? I mean, you shouldn't really necessarily think about this as like a program so much as it is like a specification of a constraint system that you're going to allow people to prove satisfaction of. So like, it's like a constraint.
Constraints.
Yeah.
Okay. Thank you.
Okay, so everyone feel good about this simple example? All right, let's get to some slightly more complicated programs. And then the other thing that's kind of cool is that like you can press Command S to save as a GitHub gist, and then you can like return to it later. All right, so the next circuit that we're going to try to do is we're going to try to do num to bits. So what is num to bits? Well, basically, one thing that I often care about doing in like computer programs is various binary manipulations. So for example, if I'm like calculating a hash function, like the SHA-256 hash function, then I'm going to need to be operating like on these bit strings and doing things like XOR and bit shifts and stuff like that. However, kind of like I mentioned on Monday, we're working in this programming model where like our atomic units of computation are prime field elements. They're not zeros and ones. Like under the hood, these mathematical objects are elements in FP. So there's no notion of basically like what is the third bit of this number. It's just like we're working with different mathematical objects. So one kind of circuit that is very useful in a lot of ZK programs is a circuit that converts one signal into an array of signals that are all either 0 or 1, like specifically, let's say, like the additive and multiplicative identity, such that when interpreted as like numbers in Z, this is a valid, bit string representation. So what we're going to do is we're going to write a circuit that takes in as input a value in, and basically like outputs these four, well, we're going to consider the function that basically takes in as input like a number between 0 and 15 inclusive, and outputs four numbers, each of which is either 0 or 1, which when concatenated together is the bit string representation of the input to the function. So that means that we've got 5 variables that are involved. In our circuit here, and we're going to try to figure out how to constrain them. Oh, yes? Oh, yeah, thank you. We're going to try to figure out how to write constraints such that the only way these constraints are satisfied is if these numbers are indeed the bitwise representation of in. Now, the thing that I've written on the screen here, like assuming that I write all those constraints properly, is really not that interesting. Like what this essentially would compile to is a zero knowledge, is like a zkSNARK that allows me to prove like I know a number such that like its bit string representation is 1101, but I'm not going to tell you the number. So by itself, it's not that interesting. But the first thing is that it's a useful kind of toy example again to get a grasp of the concepts around ZK programming. And the second thing is, like I mentioned, the way that we build these more complex functions is out of these smaller building blocks. And what we'll show later is how to take this like building block and like incorporate it into another function. Yes, Madars, did you have a question?
It's a range proof, so it's actually is useful, right?
Yeah, so this is also, like, I'm saying this in isolation. Like, if I compiled, like, a proving key off of this. Other questions? Okay, cool. So, can someone give me, let's just start purely abstractly. What is an example of an equation that must be satisfied if B3, B2, B1, B0 is the bitwise representation of in? Let's go in the back. What's your name? Sorry? Amir. Yes, Amir.
Just 2 to the power of the digit sum is the geometric sum is the
Cool. Can you help me write that out? So I'm going to write in is constrained to equal what?
So B0 is the leading digit, right?
Mm-hmm.
It's going to be B0 times 2 to the 3.
Oh, sorry. B3 is the leading digit.
Then it's going to be B3 times B to the 3.
So I'll write 8 times B3.
Plus 4 times B2. 2 times B1.
Cool. All right, so this is one such equation. One thing I'm going to note here is that, like, previously I said to you, oh, the only equations that are allowed are of the form A equals B plus C and A equals B times C. That's kind of a lie. Basically, any, like, degree 2 or less equation is going to be acceptable, and the compiler is going to figure out how to break it down into the sequence of equations that are admitted by the particular constraint system that we're working with. So actually, you can model this as basically, like, the compiler, and thus the language, is like a little bit more intelligent and allows you to not have to write this as a sequence of like, first write like temp1 is constrained to equal b1 plus b0, and then temp2 is b1 plus temp1, and then temp3, et cetera, et cetera. So we can write like linear equations. Quadratic equations are also acceptable in a certain form. Quadratic equations that don't have like more than one quadratic term particularly. Okay, can someone give me another or actually, well, here's my question. Is this enough? Because this is the equation for like just the binary representation of a number. In the back, yeah, what's your name? Noah, yes.
You also need to know that each of the individual bits is either 0 or 1.
Right, yeah, so as Noah points out, we need to know that these are actually bits. Otherwise, we can have bad cases like you can have like in is just equal to B0, and then the rest of these numbers are 0, and like that's not a bitwise representation at all. So we need somehow to write some equations that help us to make sure that these are bits. Does anyone have any ideas here?
So 0 is equivalent to either 0 is equivalent to B0 times B0. B0 is equivalent to B0 times B0.
Yes. Okay, so as Joshua says, there's a quadratic equation that we can write down, which I'm going to slightly rearrange, that will ensure that B0 is either 0 or 1. So that equation is this. Okay, so yeah, this is a quadratic. Polynomials and roots in FP work exactly as they do in Z. So this equation appears to have these two roots, 0 and 1. So that means that like the only way for this to be satisfied is if B0 is a bit. So what I'm going to do is I'm going to copy over that constraint for the remainder of these values. Oops. And now I've got these 5 equations over here. So is this enough? Are these enough equations for me to be sure that there's this particular relationship between the BIs and in? Raise your hand if you think no. Raise your hand if you think yes. Okay, cool. So yes, the yeses have it. This is indeed a sufficient constraint system that allows me to get like the bitwise representation of a number. One thing that Madar has also alluded to was the fact that actually this also serves an auxiliary purpose. At the beginning of writing the circuit, I said, let's just assume that in is between 0 and 15. Well, as it turns out, one side effect of satisfying these constraints is that the only way to have a value in that can even like take part in these 5 equations is if that value in is between 0 and 15. If in did not have a 4-bit representation, then there would be no way to pick 4 values that are either 0 or 1, such that their linear combination in this form equals the value in. So that's also another useful trick in general, and it's called a range check. Okay, so let's try this on some like sample input here. So we're going to say in is like 11. And we're going to say B0 is 1, B1. And the representation of 11 is 1011. So we're going to write these for the B's. And then I'm going to press Shift Enter. And I'm going to get, oh, oops. Let me see what's going on here. On the input? I think I have a closing brace here. What's the position 6?
Is that where it's from? Isn't that 1, 0, 1?
The leading digit is B3.
Oh.
So the most significant is B3.
Oh.
Let me just... Does this look malformed somehow to anyone?
Yes, your opening bird, like.
Oh. That's like some other, yeah, okay, cool, thank you. Everything went okay, Circom safe, and no errors about assertions, so this is valid. Again, we can check what happens if this is not actually the binary representation of in, we get assert failed. Okay, so far what we've shown is like this like super low level way to write these constraints. Circom is a little bit more powerful than that, not that much more powerful, but it does allow us to do things that prevent us from having to do like a bunch of really tedious tasks over and over. So for example, for some operations, we're going to be wanting to operate on like 32-bit or 64-bit numbers. There's just, most programs are more complicated than just turning a number into 4 bits. And it would be really annoying if every time I had to do that, I basically had to write out this like system of like 16 or 32 or 64 equations. So the first thing that I'm going to introduce here is syntactic sugar that allows us to write with like arrays and for loops. Because a lot of times what you're going to find is that like if you're writing a constraint system, a lot of these constraints are similar, and you'd like tools to just sort of automatically generate all of them at once. So the first thing that I'm going to do is I am going to turn this into a sequence of array elements. So instead of this, I'm going to write signal input B4. Oops. All right. And then I'm going to replace each of these with basically like indexing into that array. So I can press Shift-Enter. Oh, and then the other thing I'm going to have to do is I'm going to have to change this input, because now this input format is wrong. And you can see that zkREPL is just like complaining a lot. So we're going to make this 1, 1, 0, 1. Yes, that's right. Good catch. Cool. So now this works. Actually, sorry, before I go on and just talk about language features, one more thing that I want to like identify about this circuit that we've just written that's interesting is like, now we're starting to get into the territory of figuring out like, we've got these computations, we've got this very simplified constraint system model. How do we find equivalences between like computations that humans care about and like this constraint system model? This is not at all how we would like think about deriving the bit representation of a number, like if I'm like writing like Python code or something like that. So a lot of the game of ZK programming is figuring out like, all right, like again, rather than bits, I've got field elements, and rather than like, functions that I'm used to, all I have is like plus and times, like these arithmetic operations. How can I come up with some clever polynomials, basically, to encode the thing that I want? So we've seen that now in the example with like representing a division or a multiplication by modular inverse as an arithmetic constraint, and now we've seen this with this like bit thing as well. And this rabbit hole basically goes like super deep. So you can kind of imagine like writing all sorts of like exotic primitives and functions and stuff like that by being particularly clever about how you set up these like polynomials. So anyways, back to language stuff. Okay, so what we wanted was some way to make it so that I didn't have to write out each of these equations that like look basically identical. So Circom has the concept of a for loop. So it works pretty much how you'd expect. And I can write this. Cool. Everything went okay. Circom safe. No errors. So this is a lot better than what we had previously. But there's one more part of this like code snippet that doesn't scale with the number of bits that I care about like bitifying my input to. Can anyone tell me like the line number that's going to be a problem?
11.
Yep. So yeah, line 11, this is still going to be really annoying. If I have to write out by hand like the value of 2 to the 64 times b of 63, et cetera, that's going to be kind of a nightmare. So what Circom also allows me to do is there's this like syntax for accumulating linear terms into a big linear sum. And what that syntax is I can use basically a variable that stands in for an expression. So I'm going to start off with like var accum, and then I'm going to write for, this counter. I'm going to say accum plus equals 2 to the power of I times bi. Okay, so I've got my accumulator variable, and what's basically going on is this is just syntactic sugar for saying like, roll up these terms into a single linear expression. And at the end of this, like what I'm going to write is in is constrained to equal accumulator. And what this is basically saying is that like accumulator has rolled up like these 4 terms. So under the hood, this is basically just getting like blown up into exactly what that expression is. Does this make sense? Yes, question?
Are variables 0 initialized by default?
I believe so, yeah. I mean, we can see what happens if we do and don't do that. So let's press Shift-Enter. It looks like this is fine. Let's see if this is fine also. It looks like that's fine too. Yeah. Maybe it's safer to 0 initialize them, actually. I don't remember off the top of my head. Okay, and so with that, we have this like much more scalable function, right? Or much more scalable circuit constraint system. And we can do things like, it's really easy to modify this to be a circuit that takes in like 5 bits. And converts into a 5-bit representation like so. There's still kind of one annoying thing, which is that like I had to change that number 5 like all across the function, all across like the constraint system. And again, like one reason that we build these kinds of circuits is so that way, like, this is like a building block circuit. It might be used somewhere else. It might be used somewhere where, like, you have 128-bit bitifying that you want to do. You have like 64-bit bitifying that you want to do somewhere else. So the thing that we're actually wanting to do is like the dumb thing here would be if I had to write my circuit library to have the version of this with like 1-bit, 2-bit, 3 bits, 4 bits, 5 bits, et cetera, et cetera. So we're going to make it so that we can just parameterize 5. And the way that you can do that is you can see that like this template, like this is a constraint system template. It's not actually like it's neither an instantiation of a constraint system, nor is it like, a particular set of equations. And you can parameterize templates, and we're going to parameterize this one with n bits. So now what happens is if I ever write example of 5, then that's going to be taken to be like a particular instance of a constraint system that is built off of this template parameterized by like n bits equals 5. So now this works, and you can kind of imagine that like, now if I want like the 64-bit version of this and I want to use it anywhere else in my code, I can just do like, let's call this num to bits also. Then I can just like plug in 64 here. I don't need to get the particular like version of this that's like num to 64 bits or something, and then num to 63 bits and num to 62 bits, etc. Just have that parameter. Cool. So that's num to bits. Any questions? Noah?
I took a look at the R1CS file. It looks like it's just like a binary blob. I was just curious, like, to what extent it's possible to decompile that, like the thing that's actually getting loaded into zero-knowledge proof back to something that looks like Circom.
Yep.
I had an idea of how that might work initially when you were looking at like just a raw translation where you're like writing all the constraints, but once you get to the point where you're
Yeah. Oh yeah, no, this is a great question, and like there's like a bunch of like branches that we can go down here. Okay, so the first thing is that if you look at the like Circom repository or the ident3 organization, somewhere in there you can actually see just like the spec for the R1CS file. So you can see like it's broken up into something like 10-ish sections, and like each section, like some of these have metadata, others are like have a specific format for like encoding the constraints. So if you want to back those out, there's like tools that people have written for that, and actually in the Discord, we can point you to people who can help out with that or have written like scripts for that. The other thing is that like, all right, is there just like a straight up decompiler that goes from the R1CS into this? Like this is pretty low level. You might expect that that's possible. Well, there's a couple of things that are like a little bit tricky about that. The first is that the compiler does do a couple of like somewhat naive but real optimization passes. Maybe one more thing that I'm going to mention is like, what is it optimizing? Well, one thing that you'll notice in this like bar on the right is it spits out all this metadata about the circuit. In particular, one of these is nonlinear constraints. So the cost model here is you can effectively think like about like in this particular zkSNARK protocol that we're working in, different protocols have different cost models, but in this one, the cost is simply the number of quadratic equations, the number of equations with the multiplication in your constraint system. So the compiler is basically going to like figure out where are some intelligent places where you can actually rewrite these like 3 quadratic equations as 1 quadratic equation by like grouping terms or doing stuff like that. So that makes it like a little bit hard to like break it out, but someone actually has written a tool for doing that and like reducing all of those into their like very simplest components and then performing analysis on that. So another project from like a program that we did a while back is this program called ECNI, which basically analyzes R1CS files. So it'll take R1CS files, and actually what it will try to do is it'll try to look for like missing constraints. It'll try to determine like, is this R1CS like constraint system going to admit a single solution? Or is it going to allow like a malicious prover to come in and like plug in a bunch of like bad stuff? So that's a good thing maybe to touch on really briefly as well, is like what is the failure mode of this kind of programming? Well, let's go back to these slides. let's say that I'm looking at this function, and I, the person in charge of like writing the circuit that eventually everyone is going to use for, like, whose artifacts everyone is going to use to prove, you know, execution of this function, I forgot this second constraint, right? So what people think they're proving is that they like have an input that executes this function. What they're actually proving is like satisfaction of these two constraints. What is like the failure mode here? Like what goes wrong if I forget this second equation? Mm-hmm.
You can specify inputs that don't match the criteria you think they match, but still are still validated.
Right. So I can generate proofs basically that are going to be valid according to a verifier who's not like looked closely at what exactly they're validating. The verifier is going to think that they're verifying, you know, they're going to think that they're verifying that I have inputs, private inputs to this function. In reality, I could just be, you know, the system's under constrained. I have at least 1 degree of freedom, if not more, to just set some variables to be like whatever I want. And so that's going to be really bad if you're like, if you've got some like financial application that depends on, you know, providing a valid zkSNARK proof in order to withdraw some money. Okay, so I want to introduce a couple more things here as language features that will, you know, help your zkSNARK programming journey greatly. So one thing that you've noticed here is that, you might have noticed here is that like, right now it's on the user to define and provide all of the variables involved in the calculation. But it's also the case that like, at least if the circuit is properly constrained, a lot of these variables can be deterministically generated from other variables. Like right now, the snark machinery is not making any distinction between these 7 values, and it shouldn't be. That's like not the snark machinery's job. But semantically, like as a human, I kind of know that these are input variables that I provide. These are like intermediate values that like I have some, you know, sense in mind of how I want to deterministically generate those from the input values. And then I've got these like output values here, and output semantically means like a public derived variable, right? So you can kind of imagine for like really large computations, especially computations that involve like a lot of like turning stuff into bits and then like back into numbers. It would be like pretty annoying if I had to supply like every single intermediate value of my computation in as like an input. Like at some point, I'd probably have to write my own like Python file or like script to do that, just to like generate my like input JSON. And that's pretty annoying, and it seems like something that like can kind of live in and be taken care of by the Circom snarkjs stack. So basically, like this is some, and one last thing I'll say here is that like this is a process, you know, auto-generating those inputs is a process that's completely independent of the constraint system. If you have a bad constraint system, like, you know, you're going to have bugs that in terms of like other inputs are admitted, but like let's just focus on like completely independent of the constraint system. As a utility, how can we make it so that it's like easier for the developer to not have to provide in like every single intermediate value? So the thing that Circom allows you to do actually is it allows you to specify at proving time certain variables that are derived from inputs and default values that they should be assigned when you're creating a proof. And the way that Circom allows you to do that is with a different operator, which is the single arrow operator. So let's take a look at how the single arrow operator works. And I'm going to go back to the example where we had like some toy values here, so we can go through this step by step. 2, 4, 8, 5. And then we had okay, so the way that I can basically specify that some variables like I don't want the user to have to specify. I want Circom to provide like a default value at proving time, is I just delete the input keyword. And so I just declare these as signals. So these then are interpreted as like intermediate signals whose values should be auto-generated by Circom at proving time. And then what I'm going to have to do is basically I'm going to have to tell Circom how at proving time it should generate those values. So over here I'm going to write constraints, and then here's how to auto-gen like intermediate values. So by using the single arrow operator, I can like write expressions that like perform this auto generation process. So here I'm going to write y1 should be generated as x1 plus x2, y2 should be generated as this, and out should be generated as y2 minus x4. Cool. And let's kill this. The other thing is you're going to want to kill all the stuff after main for reasons that we'll talk about like very shortly. Okay, so now we have basically this thing that allows me to just specify x1, x2, x3, x4. Yeah, Noah? Oh, sorry. Yeah, thank you. That's a typo. Cool. So now we have told Circom that the user, like their default behavior should be to only have to specify these 4 values. In reality, the snark's going to take in 7, but like we're going to say like we're specifying like at proving time how those other 3 can be like, you know, given default values. So I'll press Shift Enter, and everything went okay. Circom's safe. The last thing that I will mention here is that, or second to last thing that I'll mention is that right now the default behavior of signals is to be private. So we currently have a snark that proves that like I have some 7 secret values satisfying these 3 equations, but I'm not going to tell you what any of them are. And like that's not really like that interesting. You know, we wanted to declare out publicly to the verifier. So what I'm going to do is I'm going to use the keyword output, which declares that out is a like derived signal that should be made public. A derived signal that should be made public, like semantically in the context of a zk function, is essentially like an output of some computation that you want to reveal to the verifier. It's something that comes at the end of like doing a bunch of steps, and then you make it public. So that's why it is called an output. And now you see that we get this nice little like area over here that says like output out equals 43.
What's the difference between this and the public keyword?
Yeah, so basically the public keyword only applies for inputs that you want to make public. So sometimes you care about saying like, I am computing like this, well, okay, so snarks are not going to distinguish between like inputs and non-inputs. But as humans, it is helpful for us to sometimes think about things as like, some things are inputs to a function, some things are intermediate values, some things are outputs, some things are private and public. And I mean, maybe I can draw like a little table or something actually. Does this show up on the? Okay. So you can kind of imagine this like 2x2 quadrants where you've got like, for the snark, the snark understands some signals to be public and private. And the user semantically, when we like think about a function, we think about some things as inputs and other things as like deterministically generated from those inputs. Some of those are like intermediate values, some of those are outputs. So private inputs, you just use signal input. Public inputs, you're also going to declare signal input, but at the very end, recall that you had this like like array at the very end of the inputs that should be like made public to the verifier. Derived private inputs are just signals. And derived signals that are private are just signals. That's the default behavior signal. Derived signals that are public we call outputs, because in practically all cases where we like derive something and then make it public, that's effectively like, an output. Now, this seems like a little bit weird and arbitrary, but once you start writing more ZK programs, it will become clear like why this actually is a pretty natural like model for thinking about this. Yeah, Neha? So, yes, from the snark's perspective, all 7 of these values are actually provided like into the proving machinery. What this is just a language level feature, essentially, that allows me to, or not, it's not really a language level feature, but it's a feature that allows me to also bundle in this thing that I would ordinarily have to do with like a Python script to generate those 7 values.
I guess I understand it for the intermediate values, but out is important because you had to sort of pre-commit to it ahead of time, right?
Yes, and you still are pre-committing to it ahead of time. Like before you've run any of this proof, like you're coming up with 7 values that you're supplying to like the prover black box. Yeah, it's not going on here. It's going on like over here. Like that's in kind of like user land. But this is just allows you to do that for convenience. Yes, what's your name?
Serena.
Serena. Mm-hmm.
And questions like a bit about syntax.
Mm-hmm.
I looked up the syntax for Circom, and it seems like the /* is like a comment. So I was wondering why like we put input in a comment and why that's still like right.
Oh, yeah. Again, this is like not a Circom thing. This is like a zkREPL thing. zkREPL will just like scan the page for something that looks like this. I mean, ideally this should actually be in some other like, modal or something like that, but yeah, just for convenience. Emily.
Yeah, so I have a question about like auto-generating the intermediate values.
Mm-hmm.
This kind of like assume that you would know the valid input, because like if you were to input into the snark like something that does not satisfy the equations, like but then we use this proof instead to like auto-generate the intermediate values. So would that kind of like imply like you're already kind of like pre-solving the snark, if that makes sense?
Yeah, okay, so one way we can take a look at that is like we can look at the failure modes. So one failure mode here is like this, again, it's just telling you how to provide like some 7 values, 3 of which are derived into the proving machinery. The proving machinery is proving this stuff. Like it is on the user to figure out whether or not this generates something that will satisfy this. So right now it does, but if I did this, then it would be like assert failed. So like the values that I'm generating are like bad. Does that answer the question? Cool. So, okay, one last thing that I'll show here is that, actually, okay, 2 more things I'll show. The first is like we can look at that function where we were doing like division, where the constraint looked like y1 equals y2 times x3. Constraints can only involve arithmetic operations, plus and times. But again, like at this auto-generating step, this is like totally just on essentially like the user, like pre-proving step. So these expressions can involve any operators that we want. And there's a syntax also for like making these like, functions that basically look like regular, code in the regular programming model. In particular, if we tried to do this, and let me just write out like 4, 6, 2, 1. If we try to use like a division operator in like the in a constraint, I'm going to get some error which basically says like, non-quadratic constraints are not allowed. Like only operations with plus and times are allowed. So it's going to be the case that to constrain a division, I am going to have to do this. However, this guy can use whatever operators it wants. Use bit operators, anything like that, because again, it's just specifying like pre-proving time, like how do I pull together the set of variables. So I press Shift-Enter here, and this is fine. 4 plus 6 divided by 2 minus 1 is indeed 4. So this is okay. All right, so one more thing then I'll show here is in a lot of cases, you'll find because a lot of constraints are indeed arithmetic constraints, or because they're using like templates, which are basically these like modular building blocks, or sorry, instantiations of templates, which are these modular building blocks of code. In a lot of cases, the constraints that we write and the like witness assignment that we write is going to be like similar looking or even identical expressions. So in those cases, what ends up happening is that there's like a syntactic sugar that I can do, which is I can use something I can use an operator, the double arrow. So actually, let me do this. So double arrow is basically just shorthand for like break this up into a constraint and a witness variable assignment. And yeah, it's just like purely syntax that ends up being like compiled down effectively into these two things. So all of this essentially helps you to like write circuits that are more readable. And when you're like reading a circuit that just has these three lines, you can basically read it as like, okay, y1 is constraint equal x1 plus x2, and I basically just don't even have to think about the witness generation. And then y2 looks like this and out looks like this, and it starts becoming a little easier to reason about because it feels a little bit more like top-down programming. Yeah, so the last thing also maybe here is that like I can't do this because this would try to compile down into like this, and like non-quadratic constraints are not allowed. So if I do have statements that require me to like generate some intermediate value with something that's not a plus or times, I'm going to have to go back into like the single arrow regime, single arrow and constraint separately regime. Or in that num to bits example, there's no way that I can like write like a series of those expressions in such a way that like I could just use double arrows. Yes, Serena.
Two questions. One, is it guaranteed that y1 is equal to x1 plus x2 if that's how we're defining it? And two, when we were running it earlier, it seems that linear constraints is always 0. I wonder if there's some weird thing with the language or is that a
Yeah, what it's basically doing is like it's like the compiler is doing this optimization where it's just going to group the linear terms together, and you can like write that whole function again as just like a single quadratic equation. So the compiler just like figured out how to do it and end up with something like this. Regarding your first question, again, what's going on under the hood here is this is just syntactic sugar for those two lines, which are actually doing two separate functions. One is a constraint, and one is like a witness auto-generation. Does that answer the question? Oh, actually, so let me take this one step further, which is that like that means that double arrow is like very safe. Like you're never going to end up in a situation where like if you're only using double arrow in your circuits, then you're going to end up with a situation where, like you said, the auto-generated values can only satisfy the constraints, which is actually what you want. Like you don't want to admit solutions that you don't expect. So that's really good. Double arrow is very safe. So in general, it is preferred to use double arrow whenever possible. I've just broken this down so that way, like for like learning purposes, we can kind of understand what's going on under the hood. Yeah, Noah?
How common a bug is it for people to need to use double arrow and instead use single line arrow and not actually generate a constraint?
Yeah, so there's like a lot basically of like ZK beginner kind of issues around this thing where people look at some code and they're like, oh man, I can't use like division or bit operators. Well, let me just change this to like a single arrow. And, like that doesn't make any sense. That doesn't work at all. That's not what like the programming model here is. Which is why we go through this like whole kind of like 90-minute thing. Like, we've like iterated on this explanation many times because explaining why you can't just have a circuit with single arrows requires you to have like the mental model for what's going on under the hood. Okay, so one more language feature that I want to show. Oh, actually, here's an exercise. Let's make it so that this is an output, i.e. like this is derived. So I'll show that real quick because I know we're running a little bit low on time. But basically what I need to do is if I would like to make it such that like it's not on the user to have to like supply B here, then I'm going to write like some single arrow expressions that like pre-proving time are going to tell like the library how it should auto-generate these values. So the way that I'm going to do that is I'm going to write for var I equals 0, I less than m bits, I plus plus. So this is how I'm just going to go through each index in the array and assign it to like its appropriate bit value that like it should be, like pre-proving time. This is the thing that I want to supply to the prover that ought to satisfy these constraints. So here I'm going to write bi single arrow. Let's go in backward slash is integer division. So I'm going to do integer division 2 to the I mod 2. And I can't use this, I can't use this, I can't use this in a constraint, but that's fine because we're just generating the witness. Also, I've been using the word witness a lot. Witness refers to the set of all signals that are passed into the prover. Oh, yeah. And then this no longer needs to be like here at all because I don't have any public input signals. Cool. So now we see that I have like assigned like pre-proving time. I've specified how to generate like my inputs, and then I've specified what constraints is the snark proving, and I can see like these are my outputs and a valid proof generated. Yes. Sorry. Name again. Farid? Yes. Farid. Yeah, there's bit shift operators also. I'm just like not using them here, but you could just bit shift actually. Cool. All right, any questions so far? Okay, so the last thing that we'll show here is we're going to show, like I mentioned, and like you can see in the syntax here, this is a template, right? And what that kind of implies is that like it can be used as a building block in other circuits. So we're going to show how to use that as a building block in other circuits. So I want to generate a zk proof for the function that is like, I have an input x, I take its second most significant bit, or let's say second least significant bit, I've added 3 to it, and I've gotten this output. And I'm not going to tell you what my like starting number was, but I'm going to be able to provide a zk proof that like after doing this process, which is kind of contrived, but for the sake of example, I got this particular output. So that's something that involves like this kind of like subroutine, basically, of having turned a number into some bits. So let's look at how I would do that. So I'm going to say I have some signal input in, and then I've got some signal output, let's say out. And I want out to be the second least significant bit of in plus 3. One way I could do that is I could just like copy paste this whole thing straight up into here. And notice that also this template tells me like simultaneously how to generate intermediate values that are like appropriate, as well as provides me with a set of polynomial constraints that I need in order to ensure that the input and the output of this like template are appropriately matched. So what I can do is I can basically like abstract that routine like entirely away into its own like sub thing. So I'm going to write is component bitifier equals num2 bits, and let's say that we're working with like 5-bit numbers. That's kind of like that's all that our protocol is equipped for. So what I can do here is I can write bitifier dot in. So that's another thing about the input signal. The input signal allows me to basically like connect a wire into this like sub-component of the whole circuit, this sub-circuit. Bitifier dot in, I'm going to assign in to be that. And again, this notation basically says like I'm connecting this wire, which means I'm constraining this signal to be the same thing as the signal labeled in this instance of num to bits. And then also at like, witness generation time, I'm also going to like auto-generate that value appropriately. And then what I'm going to do is I'm going to do out is going to be bitifier.b1. So that's the second, like again, I can do that also because this is marked as output. That's how I pull a value out. That's how I connect a wire from the output of a subcircuit component. I'm going to say +3. Does this make sense? Cool. Then I can press Shift-Enter, and I can, I need to make the main function of this main. Press O. This happens sometimes, in which case just like refresh the page. Okay. And then I get out equals 4, which is what I expect. And that's basically like how you can start composing all of these circuits together. So with that, we can finally look at like the default front page auto-generated example on zkREPL, which is like got all this extra stuff. So what's going on here is that like this default kind of example circuit is importing circuits from Circom, which is a standard library of circuits that contains things like the Poseidon hash function, which is a snark-friendly hash function. It's a hash function whose total number of like multiplications is like very small in this, FP model, because it's specifically been engineered to use only a bunch of plus and times operations. And then it like computes a hash and like constrains various things, and we can like break this down if anyone's curious about this in office hours. The other thing that I'll mention for today is that the exercises that we have for this session are like we've just done num to bits, but the exercises for this session involve like writing circuits for other like really common operations. So these are things that are like really, really low level. Like one thing that you have to do is you have to figure out how to write is0, which is a circuit that outputs 1 if the input is 0 and 0 otherwise. And that actually turns out to be a little bit of like a tricky problem that we'll like leave for people to think about. If you have questions about this or want to discuss it, feel free to like discuss in Discord or come to office hours tomorrow if Jason, you're cool with also talking about circuits in addition to zkML. But yeah, otherwise like we're available on Discord. Or you can come to office hours on Tuesday as well, and we can talk about these things before Circom 2, which Vivek is doing next Tuesday. But these are the exercises that we'll leave people with. Sorry we didn't get to the applications, but I have a bunch of links about the applications in the lecture notes for today if you're curious to dig into like how do you go from something as simple as this to something that's like decentralized StarCraft, which is Dark Forest, or a cryptocurrency anonymizer, which basically allows like anyone to like mathematically anonymously transfer digital currency, or like, yeah, other like complicated things. But that is all for today. Thanks, everyone.